Welcome to the Chapter 6 lecture for Management 3120 Operations Management course. I am Dr. Bill Perkins, and I'm going to provide you a video lecture based on the material found in the textbook Practical Operations Management, 2nd edition from Natalie Simpson and Philip Hancock. So our objectives for this chapter include defining process strategies, recognizing facility layouts, and creating facility layouts. So let's get started. Processes are actions that transform into outputs. Thus, process strategies are differing approaches toward that transformation. The three basic strategies for processing inputs into finished products are make to stock, make to order, and assemble to order. A make-to-stock operation transforms inputs into highly standardized products. It is a system that produces high volumes of standardized product. And as figure 6.1 here illustrates, this process strategy consumes raw materials and works uninterrupted to create a stock of finished goods. The assembly line is a familiar form of make-to-stock production, producing goods that can be stored for later consumption by the consumer. And make-to-stock systems emphasize the efficiency and high volume production associated with mass manufacturing. A high degree of standardization of the product also implies a high degree of standardization of the processes, providing opportunities for specialized equipment and automation. Although make-to-stock system does not produce instantaneously, lead time as perceived by the customer is generally instantaneous because the finished good is available off the shelf at some retail location. Thus, consumer goods are often produced by make-to-stock operations. The extreme version of this approach is continuous processing, where a single product is produced in great quantities by uninterrupted flow of inputs through an operation such as the refining of gasoline from crude oil. In a make-to-order processing strategy, transformation does not begin until the specific customer demand is unknown. This delay implies longer lead times for customers who must then wait while product is created according to their specifications. And figure 6.2 on this slide shows the pattern typical of a make-to-order approach to goods production, in which a system begins with a stock of materials, similar to figure 6.1 a couple of slides ago. It does not accumulate substantial stocks of inventory elsewhere. Each unit of finished product is assumed sold to and removed by the customer who triggered its production. And the purpose of a make-to-order system is to provide a customizable product. Any custom-made good is created through this lower volume process, and most services resemble make-to-order more closely than make-to-stock. In either case, the lower volume of production generally results in higher costs, and this translates into more expense to the customer, such as the higher fares paid for taxi versus bus service. Assemble to order, or ATO systems, attempt to combine the benefits of make to order and make to stock, also known as make to assemble, options oriented, or modular. And assemble to order strategy uses a make-to-stock approach to generate standard sub-assemblies, also known as work in progress, which it then uses to meet specific customer requirements in a make-to-order fashion. And the purpose of this combination, as illustrated in figure 6.3 on this slide, is to offer variety to the customer while reducing customer lead time and gaining some of the efficiencies to make-to-stock production. Conceptually, fast food restaurants provide visible examples of assembled order. These organizations generally divide their operations when busy, with some personnel focusing on the production of a constant stock of work in process, such as cooked meat patties and unpackaged fries, while others focus on assembling specific meal requests as customers arrive. So the custom kitchen purchased by this couple is in fact a blend of stock components and a broad choice of finishing options, which the customers select in this planning session with a production representative. This gives the customers the impression of a product that was made to their order and yet available rather quickly, while the producer enjoys the lower costs of a make-to-stock operation. A product layout is a configuration in which transformation proceeds along a single unchanging pattern through a facility. A product layout is defined by a single unchanging traffic pattern through the facility, as illustrated here in figure 6.4. This unchanging pattern marks the flow of transformation, creating a highly standardized product, the logical choice of layout for a make-to-stock production. One familiar example of a product layout is an assembly line, although not all product layouts fit that description. As the name suggests, what all product layouts do share is a devotion to the efficient production of a single standardized product. The fundamental advantage of a product layout is high efficiency. This efficiency results from an unchanging pattern of processing designed to transform high volumes of standardized inputs into high volumes of standardized output. Other advantages often associated with product layouts include relatively high utilization of resources, relatively low reliance on skilled labor, and relatively low per unit cost of production, and relatively less complex managerial planning and control required. Now, some of the disadvantages of a product layout may be controlled through good management. As an example, cross-training workers in a variety of tasks may decrease boredom and increase general job satisfaction, while simultaneously helping protect the system from disruption when one worker is absent. Mixed model assembly may also be possible, in which different versions of a product, such as an automobile, are created by a single assembly line, offering the customer some variety. Regardless how the product layout is managed, the initial design of the facility focuses on the design of its single path of transformation. Because a product layout consists of a single path of transformation through a facility, the designer of that layout must assign all transformation processes to two distinct locations along that path. Think of this as dividing the production work along the path, and the more equitable the division of this work, the smoother the operation. This design technique is called line balancing because its goal is to divide transformation as evenly as possible, balancing the workload along the path. Line balancing is an algorithm producing a design through a series of steps, and the first of these steps concerns the cycle time of the line. In a product layout, the unchanging path or line is typically organized into a series of distinct locations or workstations. Since each workstation passes product along the path to the next workstation, each should be assigned the same amount of time to complete its work assignment. This allows a smooth, balanced flow of work among the workstations, and this equal budget of time given to each workstation to repeat its assigned work is known as the cycle time of the operation. This single length of time is extremely important to product layouts because cycle time determines three things. First, the amount of time a single workstation is given to complete its work on a single unit of product. Next, the total number of workstations required in the layout. The shorter the cycle time, the less work can be accomplished at each workstation on each unit of product, and thus more workstations needed to complete all the work required. And third, the speed at which the layout produces finished product. A shorter cycle time means faster production. Any product layout cannot be designed without first selecting its cycle time. Figure 6.5 here illustrates the range of choices in cycle time available to the layout designer. At one extreme in figure 6.5, a product layout cannot operate with a cycle time any shorter than the length of the longer task to be performed, or that task would never be performed successfully. That makes sense, right? At the other extreme, the longest cycle time that makes any sense equals the sum of all the tasks to be performed, although this implies an assembly line with only one workstation completing all tasks. In reality, the cycle time is likely somewhere in between, based on the desired capacity of the system being designed. So we discuss how to derive at a target cycle time from a desired total output of the system next as the first step of the line balancing technique. Line balancing distributes work evenly along the path of a product layout, enabling smooth, rapid flow of production. Line balancing is also heuristic. It's also a heuristic technique that can produce multiple solutions, but cannot guarantee that any solution is necessarily the best answer to the scenario. As an algorithm, line balancing is best described as a set of steps. First, to determine the cycle time for the layout. Next, to draw a precedence diagram illustrating the tasks requiring assignment along the path of the layout. Next, to assign those tasks to workstations along the predetermined decision rule. And finally, to evaluate the efficiency of the resulting layout. The design of a product layout is essentially complete at the end of step 3, but since the procedure cannot guarantee this design is best, it is wise to evaluate it for comparison with other designs. And since cycle time is essentially the speed of production, the cycle time of a product layout must reflect the production capacity desired for that layout. To determine cycle time for line balancing, we must first know two pieces of information. First, you need to know the operating time, how long the line will operate. This interval can be expressed as how long each day it will operate, or how long each month, or how long throughout its entire lifetime. And next, you need to know the demand on the line, how many finished products the line must complete within its stated operating time. So with these two readings, we can determine an appropriate cycle time for line operation with the following formula, as illustrated here. Cycle time equals operating time divided by demand on the line. And once we determine cycle time, we can begin to design the design process. At this point, data must be collected on each of the tasks required to successfully create one unit of finished good. This data should specify both how much time is required to complete each task and whether any tasks must be performed in a certain order, a restriction known as a precedence relationship, which essentially means a dependency between two tasks, usually requiring that one task be completed before the other task is started. And precedence relationships can be described in a variety of ways, but one common method for communicating dependency between tasks is by specifying immediate predecessors or tasks that must be finished directly before another task is started. And the primary goal of any product layout is highly efficient use of its workstations, and thus any layout produced by line balancing should be evaluated for its efficiency. This evaluation begins by reviewing the individual workstations in design for idle time. However, the overall percent of workstation use can be calculated rapidly with only 3 pieces of information. First, the sum of the task times, which would be referred to as ST here, the cycle time, which is CT, and the total number of workstations required by the design, which would be N. With these values, efficiency of a product layout can be expressed as efficiency equals sum of the tasks, so the sum of the tasks divided by the cycle time multiplied by the total number of workstations. So you would multiply cycle time by total number of workstations, and then you're essentially going to divide the sum of task times by that amount. Now we can calculate the balance delay or percent idle time in a design by subtracting its efficiency from 1.0. However, even if efficiency is high and balance delay is low for some layout, there is still not a guarantee that these are the best values that can be achieved in that scenario. So to explore this, we can calculate the theoretical minimum number of workstations as quickly as calculated from the same data. So theoretical minimum number of workstations equals the sum of the task times divided by cycle time. And bottleneck refers to most heavily utilized resource within a system. They tend to govern the maximum pace the entire system can produce. And the opposite of a product layout is a process layout organized around processes instead of a certain product. A process layout is a configuration in which transformation proceeds along multiple shifting patterns throughout a facility. And as figure 6.9 suggests, there is no single standard traffic pattern within a process layout. Each unit of the product moves between processes according to its unique requirements. Thus, process layout best supports the make-to-order strategies, creating customized output on demand from the client. Now, for this reason, process layouts are commonly referred to as job shops when producing goods such as custom printing, cabinetry, and tailored clothing. However, this style of facility is just as common in service settings where multiple traffic paths illustrated in 6.9 represents the travel of people through the system, as in hospitals, retail stores, airports, military bases, and college campuses. And since process layouts usually do not require large amounts of capital to purchase high volume, specialized equipment, and are better able to cope with changing and uncertain demand, startup companies favor them. However, a process layout produces a low volume of customized product, creating inefficiency. So specifically, process layouts suffer these following 4 limitations. First, relatively low utilization of resources. The second is relatively high reliance on skilled labor. The third is relatively high per unit cost of production. And the fourth being relatively more complex managerial planning and control is required. Designing process layouts requires determining the best arrangement of the process given complex, changing, and even unknown traffic patterns that connect these processes during use. And a hybrid layout represents a mix of product and process layout in an attempt to gain the advantages of both. Cellular manufacturing, pictured here in figure 6.12, refers to a facility organized into multiple small product layouts referred to as production cells. And group technology refers to the organization of diverse products into families of similar production requirements. And the fixed position layout refers to a configuration in which transformation cannot move, requiring all supporting resources and processes to travel to that location. And that concludes the Chapter 6 lecture. Please see Blackboard for all this Chapter 6 deliverables and expectations, and I will see you in Chapter 7.